Good afternoon, everyone, and welcome to the oral session 5.1, Synergies with Global Challenges. Today is the first time we use this room, and some of you have just come up to Hofburg today. So I would like to make you aware that in terms of health and safety, we don't have any drill planned for today. So if you hear the alarm, it's for real. So please proceed very calmly to your nearest exit. In this particular room, we either go all the way back through those glass doors and left, or through the door that you came in and just follow the green signs for exit. So no drills today. So maybe we'll evacuate very calmly. Without further ado, welcome to this session. My name is Guillermo Rocco. I am the coordinator of the IMS division in CTBTO. My background is in seismology, even though I don't do much technical work per se today, but our division in CTBTO is in charge of building and sustaining the IMS network for CTBTO. So very, very exciting set of presentations we have today, and with some of this very useful data is put to use. That's all from me. I think I would like to introduce here to my co-convener, Professor Ch3 Whaler.
Good afternoon, everyone. Really pleased to see such a lovely big audience here. As Guillermo says, we had a very wide range of abstracts, and choosing just a few for oral presentation was very hard, but we hope we're showing you some breadth of the use of the IMS data for many other purposes. I'm a solid earth geophysicist. My main research interests are geomagnetism and electromagnetic induction, so not so much about this kind of work, but I'm also the immediate past president of the International Union of Geodesy and Geophysics, and there interacted with many different areas of geodesy and geophysics. So I'm a little bit versed in the types of science that we're going to hear more about today. I think we're just still waiting for the setup. Can I encourage you to use the app to vote? It's not entirely obvious how you vote, but what you need to do is to open the session in which you'd like to vote, and then there is then an option on the right-hand side. So there's three headings. There's information, chat, and then voting. And then if you go to the voting part, then you can do that. And there will be a prize for best oral presentation. So I encourage you to do that. And obviously also encourage you to go to the e-poster session later in the week and then vote for your favorite poster as well. Are we okay with the... No, we still need to talk amongst ourselves for a few moments longer. I'm sorry about that. We'll introduce the speaker in a moment. Joe. Well, actually, you can vote early, vote often, as they used to say about voting in Northern Ireland.
Just a comment on that. I'm glad that you asked the questions, because this session is being recorded and it's being hopefully transmitted online. So anything we say, we need to say it in front of a microphone, so we can help the recording and the people online. So there will be people around us with microphones. So when the question time comes, just raise your hand and somebody will approach you with a microphone.
And there are some in the aisles as well that that you can walk up to and speak.
How are we doing? Almost there?
And again, while we're waiting, you can use the app to put your questions into the chat there instead of raising your hand. Okay. So apparently we might be up to a little bit of almost 5 minutes more to wait. So it appears we are now ready to start. So I'd like to invite Danielle Harris from the University of St Andrews, where she's a Senior Research Fellow, to give her presentation. Did you explain about the black button? Yeah. Okay. Sorry, we just wait for it to be loaded. They've forgotten. You get extra minutes.
Time. I think they're supposed to start. Okay.
Okay, I'll get started.
Yeah, go for it.
Thank you very much. It's a pleasure to be here. Before I dig into my presentation, I do have a few acknowledgements to make that I didn't want to forget. So thanks to the Richard Lounsbury Foundation for supporting this effort. Our summer interns, Victor, Helen and Maddie, who did a great job this summer for the project, and obviously the data coming from the CTBTO. There's also another US Navy-funded project, Cortado, which I'll mention later in the talk, and you can see a whole team of people there. So this is very much not a solo effort, and thanks to everybody who's working on this with me. So the bottom line is wildlife monitoring programs are really costly, and I'm talking about whales, but there's a picture of an elephant there to remind me that this is a problem both in marine and terrestrial systems. And basically, we often want to know how many there are, and not only that, what their patterns are across time and space. And we often need these metrics for conservation and management purposes, of which there are many around the world. And so we're often looking out for cost-efficient approaches, and we sometimes call these platforms of opportunity, so instruments that are deployed not for detecting wildlife, but for other things but that we can make use of. And obviously, the CTBTO IMS is a fantastic example of a platform of opportunity from the wildlife perspective. So I'll be talking today about hydroacoustic data, and you can see the sites here on the map. There are other instruments within the IMS that have the potential to monitor wildlife, but I'll be focusing on the marine hydroacoustic systems for this talk. And particularly in the Indian Ocean, it's very interesting for marine life, particularly large whales. So I'm going to show you some spectrograms. Here we have some images of sound. On the y-axis is frequency or pitch, so higher and lower. Across the x-axis we have time, and the colors show the intensity of the sound. So the brighter the color, the brighter or the higher amplitude or the louder the sound we can see. And so what you're seeing here are different blue whale sounds. And basically, blue whales have regional accents, if you will. So depending on where you are in the ocean, you'll hear different things. So on the left, we have something called the Sri Lankan call. You see 3 units there, kind of comprised of different parts. The middle one is known as the Madagascan call. And then the final one are 6 units, a little fainter, of the Antarctic blue whale call, recorded not far off the equator. So we're hearing a lot of diversity across the ocean. Here we have, on the left, another song type which has been attributed to possibly a new population of blue whales. It's not been verified yet, but we're always learning new things. In the middle, we've got some fin whale pulses, the second largest whale in the ocean. And then finally, we've got 3 instances of a sound that's believed to be made by the Amurus whale, a relatively recently discovered species of baleen whale. And baleen whales are the bigger ones, and that's why we can hear them with the international monitoring system, just because of the sampling of the units. As most of you know, the CTBTO's a big strength is the amount of data that are available to us. So here's another spectrogram, an image of sound, but now rather than minutes on the x-axis, we've got years. So we've got 10 years of data here, and if I just show you the small insert, that's the Sri Lankan call. And if you look at it around 100 hertz and 60 hertz on the big image, you might see some faint lines. And that's the Sri Lankan whales appearing over a decade from data from Diego Garcia. So it's really powerful for wildlife monitoring, and that's why it's such a great data set to work on. So what are we trying to do with these data? We would like to turn the recordings into ultimately number of animals, and we need to do some statistics to get us there. And so there are various methods out there to do just that, to estimate these animal absolute densities or abundances, as we call them. And there are terms that you might come across in the literature, such as distance sampling, spatial capture, recapture, and they're very traditional methods for estimating animal abundance and densities, or we have to use other methods using sometimes simulations, which I'll talk about in relation to this project. But all of these methods, their key reason is to estimate the probability of detection. And this is a parameter that we need to estimate that absolute density and abundance. And so if you can see the equation here, it's just multiplication and division ultimately, but there are several bits of the puzzle we need to pull together to estimate that number of animals, big D. So we have little n, the number of detections that we hear in our recordings. C is the false positive proportion. So if we're using automated detection methods, they get that wrong sometimes. So they're not perfect. So that 1 minus C enables us to scale down the number of detections to say, okay, some proportion were not actually whale calls, they were something else. On the bottom, we have pi w squared. That's the area that we're monitoring. We have K, the number of sensors. I'll come back to P. We have T, the time monitored, and then we have R, this Q production rate. How often do these animals make their calls? That enables us to convert call density into animal density. We need to understand the animal behavior. But you'll see probability of detection there appears on the bottom of that equation. And if nothing else, the main point is that if we ignore that parameter or get it wrong, we will bias our density estimates. So all of those pieces are important, but it's important that we think about probability of detecting those sounds. I'll just try and...
Clicker. Can you click the next one?
And so why is detection probability important? Now, this is some data from the Antarctic, and this is seasonal detections of blue whales. And you can see on the y-axis, we've got mean detection rate, so simply calls per hour that we heard on the hydrophone. This isn't CTBTO data. And you can see we have seasonal numbers, and we can see that the highest occurrence seems to be in the winter. We heard more calls. So that, we would start to make biological conclusions about that. But, I think it is. But if we actually then estimated the animal density, the call densities from those same data, you can see what's happened. So we've now accounted for all those parts of the equation I showed you, and the pattern changes. And we can put some uncertainty around those estimates. So the small plot is the one on the left. That's the one I showed you before. That's just the calls that we heard. And then we've gone and estimated call densities. And you can see now it's autumn that's the key season for these animals. And when we did this work, we actually realized that was more in line with what we knew about the animals' migration pattern. So it's more linked to the animals themselves. Turned out in autumn, it was actually noisier. So we didn't hear as much. But when we corrected that through the probability of detection, it turned out autumn was when the animals are most vocally active. So that's why we try and work on these density estimation methods. So with the CTBTO, we're using a simulation-based approach based on the passive sonar equation, so how well the sound travels through the ocean. We're trying to recreate that through a simulation. So to do that, we need to estimate some bearings, some sound propagation models, some noise level measurements, and all of that work is actually coming through the Cortado project that I talked about. And then we also need to make some assumptions about the source level of the animals, how loud they are producing their sounds. And we put all this into a simulation and estimate that probability of detection. Now, there are some assumptions that we make about animal distribution, and one of the summer interns, Victor, worked on that with us this summer. We learned some interesting things. And so we'd like to focus on the Sri Lankan blue whale using data from 2024. We thought that would be a nice case study. I'm showing you data here from 2002, and if you notice that the long tone is about 100 hertz. We've got an interesting thing happening with the whales that's well documented. The pitch of their sounds is getting lower. They're lowering their frequency for reasons we don't fully understand. And so this is data from a previous study over 10 years. You can see it's declining, that Sri Lankan tone that I just referred to. And one of our other interns this summer continued to look at that decline from 2017 onwards using CTBTO data. And we're just working up a small paper on that. And so these results are then informing our automated detector development. We need to know what we're looking for in terms of the right signal frequency to then generate the parts that we need for our equation. And then finally, we do know a little bit about probability of detection using CTBTO data already. It's very interesting oceanography around Diego Garcia in the Indian Ocean. And so basically, if you look one way out from the hydrophone, one of the hydrophones, where we did some propagation modeling into the deep Indian Ocean, you can see some results from our simulation. Probability of detection is on the y-axis, distance is on the x-axis. You can see into the Indian Ocean, our probability of detection decreases very, very quickly, which basically means if we have a whale out in the deep ocean, we won't hear it on the hydrophone at Diego Garcia. However, if we go the other direction, the bathymetry is different, sound propagates better, and so we can hear things out to larger ranges. And so it's really important for us to quantify that when we're turning this into number of sounds or number of animals we're hearing per unit area. So this is all part of the work that's going on at the moment. So finally, this is an example of maximizing these data to look at marine mammal distribution over large spatial and temporal scales. We're using these density estimation methods to basically help us standardize across data sets, so we can then start to compare between sites and across years as different parts of that equation changes. And there are many studies with sparsely distributed instruments, not just the CTBTO IMS, but other ones as well. So the work going on here will help inform other projects too. Thank you very much.
Thank you, Daniel. That's brilliant. Are there any questions from the audience here? Yes, please. Can you stand at the microphone then? Yeah.
Hi, thank you so much for your talk. I was curious, could you talk a little bit more about your process in verifying that these spectral features belong to this type of whale versus something else? Thank you.
It's a good question. What we'd really like is to actually record the sounds next to animals themselves that are producing it. So that's quite a hard biological task, to be out there on the water and see the animal and also record it at the same time. But sometimes, in order to match the sounds with the species of whale making it, that's ultimately what we need. Some of these other studies where we've seen sounds that have features of whale calls, we can compare with other known whale calls and say, well, look, based on this, on these features, we suspect very strongly that it is a blue whale or some other species. But it's not necessarily easy to match call to animal. So there's a lot still to discover, definitely.
If there's no obvious questions there, I have one, which is to ask about, you showed the changing frequency with time. Do you think that's the animals, or do you think that's potentially properties of the ocean? So if the ocean temperature goes up with time or salinity changes, I mean, I can imagine it's really hard to tease out, like, seasonal variability. Is that variability in the ocean, or is it the variability in what the animals are doing, and likewise in these longer-term trends?
Again, we're not sure, and it could be both, or one or the other. So it could be the animals. There's hypotheses that perhaps the animals are now getting bigger and their voices are essentially getting lower. But then also there's been hypotheses about the ocean changing around the animals, and so we're still figuring out what that is. Yeah.
Yes, please.
You talked about the transmission of sound on the different sides in the Indian Ocean. Do you think that affects the behavior of the whales? Do you think that affects how they're able to communicate with one another?
It's also a really good question, and from a behavior point of view, we know relatively very little about these animals, and also they're communicating over big or potentially huge distances. I mean, I was looking at propagation models out to 1,000 kilometers, because that's potentially what the area that's being monitored. And if they're using those features, again, it's still an unknown.
Another question?
About the propagation again. I was just wondering if the blockage on one side is produced by the topography, basically, or is there any other kind of phenomenon that causes this blind sighting?
In this case, it's the topography. So this was using one of the northern sites, and so it was very clear that there was that blockage. But again, I think it's really useful from the biology perspective that we always remember that we have to figure out what area we're listening to. And with acoustics, that's often cannot be straightforward. So as this example showed. So yes, very useful, because actually it changes the conclusions you make about the animals. It's useful for me to know that actually I'm not listening to whales in the deep Indian Ocean. Anything I'm hearing is probably coming from the other side where the sound can propagate better. So it's very important to try and work that out.
Yeah, thanks.
I think we probably need to move on to the next talk. Just before we thank Daniel once again, you can put questions into the chat afterwards. So if there's something you subsequently think about, and we're encouraging the speakers to look afterwards and then hopefully to respond to your questions. So let's thank Daniel once again for a really stimulating talk.
Thank you, Daniel. And just for those of you who just joined us, we started a little bit delayed this session. We just finished the first presenter. We are in presentation number 2, and I would like to introduce Ms. Ch3 Promsuk, who is a scientist and researcher and who works for the Thai Meteorological Department, focusing on tsunami modeling and verification. And her presentation today is the verification and modeling of tsunami arrival time and wave height along Thailand's Andaman Sea coast.
Okay, good afternoon, everyone. I'm Ch3 Promsuk from Earthquake Observation Division, Thai Meteorological Department. So today I will present on our study on the verification and modeling of the tsunami arrival time and wave height along Thailand's Andaman Sea coast using an enhanced toast. So let me start with a brief introduction. Thailand is not generally considered a tsunami-prone country, but earthquakes do occur, mostly in the northern part of the country, as shown in the map on the left, like the green dot represents the earthquake that occur. So, however, the seismic that capable of generating tsunami still exist and can affect Thailand coastline, which is the Sumatra-Andaman subduction zone. So this is a major source of tsunami risk to Thailand Andaman Sea coast. So in the past, the Megahertz earthquake used to be occur and generate the tsunami. We know it is a 2004 Indian Ocean tsunami and have caused severe impact for people who live along the Thailand coastline. After this event, my organization got funding to establish the National Seismic Network to operate the real-time earthquake monitoring. And using the SeisComp with the TOAST module inside, the TOAST using for tsunami simulation. So the parameter in the TOAST, the default one, are designed for the large scale or the global scale and may not capture the detail of Thailand coastline. So we set out the following objectives. The first one, to investigate the tsunami arrival time and wave height along Thailand Andaman Sea coast. Second, to enhance the bathymetric resolution from the 3.7 kilometers to 0.46 kilometers using GEPCO data. Third, to refine the impact area to subdistrict level. Four, to validate the simulation results with the target observation. And the last one, we would like to provide our tsunami information to another organization to let them warning people or support the evacuation planning. Let's see our study area. So, as I mentioned before, we focus only the Sumatra-Andaman subduction zone and Thailand coastline. You can see from the map that the yellow zone represents the subdistrict that we focus on. This is the impacted area for us. So all of the subdistricts that we focus are totaling 97 subdistricts that we digitize in the QG software. And for the tsunami scenario, we generate 4 epicenters. One of them corresponds to the magnitude 9.1 2004 Indian Ocean tsunami, and we use the result from that to validate with the real target data. The remaining are the simulated event that we try to generate it for support evacuation planning. For the tools and method, as we use the SeisComp as a commercial version, they provide the tools inside. We stand for the tsunami observation and simulation terminal. It will generate a rupture area based on the Well and Copper-Smith equation, and it will calculate the arrival time and wave height using the model called easy wave. The easy wave introduced by the Kovalik and Whitmore and use the 4 parameters from the Okada. And it will generate the epicenter and then it's calculate the arrival time of the tsunami and wave height for us. So The way we do it, we digitize the new forecast zone and forecast point by QGIS. We put it in the software. We put the new grid for us that we download from the GEPCO. And after that, we run tsunami propagation simulation, and we compare the result with the target data. The picture in the up represents the shapefile data that we proceed in the QGIS, and the below it one show the simulation running in the software. Okay, the result are displayed within the RTSP format, Regional Tsunami Service Provider. Actually, the various output you can set it, but after we discussed with our team, we decided to provide two times, T1 and T3. T1 represents the time of accident of the detection threshold, which is set at 50 centimeters, while the T3 represents the time of maximum positive amplitude or the height wave arrival. The picture on the right shows you that the tsunami information that we will provide to public, they show the T1, T3 wave height and the location the tsunami will arrive. This is an example of the result that we will provide, the tsunami arrival time map, wave height map, and the tsunami information. So let's see the result from the first epicenter that we used to validate with the real target data. This is the epicenter is the same at magnitude 9.1 earthquake that occurred in 2004. A comparison is made by comparing with the result from the research by the Supasi et al. 2010. In that paper, they provide two target stations that have two times, the first arrival and maximum wave arrival in the two stations called Kuraburi Station at the Phang Nga province and Tapao Noi Station at the Phuket province. From the table, you will see that we will show the first arrival time and the highest wave arrival time. The record one shows the real time from the target station, and the model one represents the time of the model from the old bathymetry and the improved bathymetry. And asterisk represents the data based on improved bathymetry. And the gray zone represents the difference between the model and the record. So for the first arrival time, show no significance between the default bathymetry and the improved bathymetry, just about 30-minute differences, while height wave arrival shows significant. If you see between the record one and the model, the old one, they have 2 hours and a half difference, while when we upgrade the bathymetry already, it's closer. From the Kuraburi station, it comes 9 minutes earlier, and for the Tapao Noi station, it comes 28 minutes later. So it can prove that if we try to improve the bathymetry, our model is more accurate than the default one. For the earliest arrival from all of the epicenter that we generate, it shows the same result that Lamkan sub-district, Thai Mueang district, Phang Nga province is the first location that the tsunami will arrive within 1 hour. For the maximum wave height, show that they show various locations that tsunami will arrive. But if you try to look at the first epicenter, that the same location with the 2004 Indian Ocean tsunami, the maximum wave height reaching about 10 meters. Try to compare with the real data from the Ch3 et al. 2006. They went to the field and they record that at that time tsunami reaching up at Thai Mueang, Thung, Got Patong, Phang Nga province about 19.6 meters, while other area was less than 10. So for the wave height, it's our challenge in our future study. We'll try to make it more accurate. But now our team say that it's enough for the early warning stage. So it can use to warning people if the earthquake that can generate tsunami occur. It leads to the conclusion. We modify the TOS model. This is a module in the SITECOM, and we improve the new bathymetry resolution, digitize the new forecast zone and forecast point into sub-district level rather than use the old one that is larger, and we try to compare with real target observation data. So the arrival time of the first wave shows no significant, while the maximum wave height closer to the record data. Among the other simulated epicenter, show the same result that Lamkan sub-district was the first location that tsunami will arrive. Let me admit that I'm not have the basic of the hydroacoustic, but I try to validate the data with the IMS data. So although we validate our validation model based on use the local Thai gate, But the tsunami sequence also align with IMS data. As the paper of the Tolstoy Bonenso 2006, they said that T-wave will arrive at the Diego Garcia South in 32 minutes. So after that, they will reach at the Thailand coastline. So this our challenge. It leads us to our future plan that we will try to integrate the multiple bathymetry dataset for the higher resolution. Because we cannot compare the time directly with hydroacoustic data because of our bathymetry is not cover that area of that station. So maybe in the future, if I can try to expand our grid, we can compare it directly. For the second future plan is refine the forecast zone from the sub-district level into village level for the precise impact prediction. Third, to enhance validation with the additional observation data. And the last one, because now we use the default model called EasyWave, maybe in the future we will try to develop our own model or maybe TMD model in the future, make it more suitable for Thailand coastline. So I think that's all for my presentation today. Thank you very much.
Thank you very much, Ms. Chutimon. Let me just ask the floor for questions. Catherine.
So I have a question. Actually, I have two if there's time. My first one is, you mentioned fault parameters of the earthquake. Did you use the same set of fault parameters for the original 2004 earthquake and then the 3 simulations?
Actually, we tried both. We use the default parameter from the Well-Coppersmith equation, and we try to put the fault parameter from the USGS. Like the first arrival, the arrival time show no significant both of the simulation result, but for the wave height have significant.
And the simulations all use the same set of fault parameters as well?
Yes.
Oh, okay, thank you.
Any other questions?
Yeah. What do you need to change? What do you think is the most important change that needs to be done on EasyWave to adapt to, as you said, the Thailand coast in your case?
Mm-hmm. In my opinion, I think if we can develop our own model, it's more suited for my country rather than use the EasyWave. Do I answer the question?
Yeah. I was just wondering because I don't know what it comes with the default EasyWave model compared to what you would like to use.
Yeah, because EasyWave is set for the global scale. If we can make it more detailed with my country, is better.
Okay, thank you.
Thank you for your question. Any other question? I have one question, very simple one. Thank you. You demonstrated the enhancement of bathymetry has a big impact going through, I think, just over 3 kilometers to less than half a kilometer. How much further do you think is possible to take that resolution?
You mean in the future?
Yes.
Of course, high resolution require more computation runtime. If we can, in my opinion, we try to make like high resolution near the coastal line, and if it's far away, I will try to reduce the resolution to make it like, less time for running. If it can reduce to like 0.2 kilometers, or maybe it's gonna be work. Just only my opinion.
Thank you. Have you got any more questions for Chutimon? If not, let's give it a round of applause. Thank you very much. Thank you.
So our next speaker is Laurent Chiable. He's a research geophysicist at Sandia National Laboratories, looking at geophysical acoustics, especially infrasound monitoring, related to a variety of natural phenomena such as earthquakes, volcanic activity, but also anthropogenic ones such as explosions. The floor is yours.
Hello. Hello, everyone. My name is Laurent Chiable, and I am very honored to present today in this very beautiful and historic city. So I am coming from Sandia National Labs in Albuquerque, New Mexico. And today I'm going to be discussing my research on behalf of my colleagues regarding the relationship between the seasonality of sea ice extent and the microbarometer as recorded at high latitude international monitoring stations. So infrasound is atmospheric pressure fluctuations below the nominal hearing frequency, so generally between 0.01 and 20 hertz. And the global infrasound environment is comprised of natural sources such as avalanches and earthquakes, but also anthropogenic sources, including space vehicles, and of course, most important to this organization, explosions. And all of these sources are relatively confined in both source location and duration, except for what is perhaps the least dramatic, but perhaps the most problematic of them. Thanks. Which is the microbaromes, which is caused by the constant movement of ocean on the Earth's surface. Next. I'll try. And today I'm going to be discussing how environmental factors such as sea ice coverage in the hemispheres and storminess can in turn affect the microbarome, which can in turn affect our detection capacity. So microbaromes are the acoustic consequence of the same process that creates the microseisms, which are generally more widely understood. But it is noise created by interference of opposing wave trains with similar frequency on the ocean surface. So here you have a wave moving to the left and a wave moving to the right, and the product wave creates pressure attractions on the ocean floor, which travel through the solid Earth as microseisms, and that's generally what people are more familiar with. But the product wave can also create pressure fluctuations at the water-air interface, which then travels through the atmosphere and is recorded as microbaromes. So these are the dominant acoustic and seismic noise features on the Earth, respectively. And they are ubiquitously observed, and they are persistent through time, and share a similar frequency band due to their common origin mechanism. And lastly, because they are both affected by environmental conditions, they are seasonal and generally greatest in winter when there are more frequent and larger storms. So here we have a probabilistic power spectral density for 1 year of hourly recordings at an IMS infrasound station. And you can see the dominant feature here is at approximately 0.2 hertz, and that is indeed the microbarome, which is defined as lying between 0.1 and 0.5 hertz. And as you can see, it lies smack dab in the middle of the IMS monitoring band determined by treaty negotiations of 0.2 to 4 hertz. And as such, the microbarome is widely understood to already be a substantial obstacle to the IMS infrasound goals. And the problem, the crux of the matter that motivates our research is that variation in microbarome amplitudes could in turn affect our monitoring, and that is the issue that motivates the two research questions that we're going to discuss. So the first one is, does the microbarome exhibit any secular trend, which is just trend over time? And the reason why this is a particularly salient question is because the microbarome, which I discussed earlier, has been shown to be trending upwards at approximately 1/4 to 1/3% per year, and has actually been shown to have accelerated since the beginning of this century. And that trend is attributed to increasingly energetic noise or ocean conditions. And given that the microbarome and the microseism have similar origin, we suspect that similar effect may be had on the microbarome. And secondly, we are curious about the relationship between sea ice extent and microbarome amplitude. And the reason why this question is important is because strong sea ice has been shown to inhibit the growth and passage of waves, thereby diminishing both the microseism and the microbarome. And there is an enormous degree of variation in sea ice extent over the course of the year in both the northern and southern hemispheres to the tune of about 1 million square kilometers. And of course, sea ice in the hemispheres is varying not just intra-annually, but over time with a consistent decline in coverage of 0.5 to 0.75% per year over the last 10 years in the northern and southern hemisphere. So to investigate these relationships, we collected data from 6 of the highest latitude infrasound stations, and we collected 10 years of data beginning in 2014 and through the end of 2024 from 1 element per station array. So here, I-53 US in Fairbanks, Alaska, we took data from the 1 element shown in red. And of the 6 sites that we analyzed, you can see that the coverage over this period is quite good, exceeding 93% in all 6 sites. So regarding the secular trend, we calculated what I call an integrated microbarometer value between 0.2 and 2 hertz for every hour in the 10-year duration. And then we calculated the linear trend within each of these. So firstly, each of them has a seasonal variation, which is consistent with previous work and expected, as we discussed earlier. But regarding the secular trend, we do not find a consistent trend amongst all 6 of these sites. We find 3 positive trends, 2 negative, and 1 near 0. We do find when we compare with trends taken from nearby seismic sites, we find agreement, so both positive at 2 of the sites and disagreement at the 3rd. We believe that there is much more to be learned from these relationships, however, and for example, you'll notice that I-55 in the lowest row, that's a site in Antarctica, has a particularly strong trend in both the microbarometer and the microseism, and we hope to learn more about that in subsequent study. So regarding the relationship between the ice extent and the microbarometer amplitude, we have these 2 time series, and we wanted to analyze the phase relationship between them. So we collapsed this data per calendar date to data per numerical day of year, which is shown in this plot. On the x-axis, you have the numerical day of year between 0 and 366. On the left y-axis, you have sea ice extent in millions of square kilometers per year, and that is shown in the black and gray lines. And on the right y-axis, you have the integrated microbarometer value shown in red, with each thin line corresponding to one of the years, and the bold red line corresponding to the median over the course of time. So the most salient, important observation of these 2 approximate sinusoids is that they are phase offset, such that the microbarometer line precedes the sea ice condition, in this case by 2 to 3 months. Now, we did this analysis for each of the 6 sites. Here we have the 4 northern hemisphere stations on the left and the 2 southern hemisphere stations on the right. And as you will see, the northern hemisphere stations are generally better behaved than the southern. And there is a great deal of variation both within sites and across sites. But the broad observation pertinent to this discussion is that at all 6 of these sites, we found an approximate 2 to 4 month phase difference between the integrated microbarometer and the sea ice condition. So we take this as evidence that sea ice is not the primary driver of microbarometer amplitude. And again, there's much more to be learned from these from this data, but that is the primary conclusion we are taking for the purpose of this discussion. So this work is largely preliminary, and we have a great deal more work that we hope to do. However, for our first question, we find it inconclusive so far. There is not a primary relationship consistent to all the sites that we analyzed. But regarding our second question, we do believe this is an important finding, that sea ice is not the dominant driver of microbarometer amplitude, and instead we believe that microbarometer amplitude is being driven more so by the storminess conditions over the hemispheres, such that the northern hemisphere is stormier in the northern hemisphere winter, and vice versa for the southern hemisphere. We hope to continue this work. We want to analyze more IMS infrasound stations. So far we have analyzed 6 stations, 10 years each, and that is admittedly a relatively small subset of the available data. So we would like to analyze data from all 53 IMS infrasound stations, and we would also like to analyze the full period of record available for each of those stations. The earliest IMS infrasound records go back to 2001, which 24 years is a pretty decent record. And lastly, we would like to consider narrower and different passbands. So as I discussed, my integrated microbarometer value was between 0.2 and 2 hertz, which is not the microbarometer per se. We want to analyze the strict definition of the microbarometer, 0.1 to 0.5 hertz. But we're also interested in other passbands to understand other sources of noise. So with that, I thank you very much, and I am happy to take any questions.
Thank you very much. Is the question here? Just getting the mic.
Yes, thank you. And on your last point, I think that's very important, because if you start at 0.2, you cut right through the microbarometer peak. So when we study microbarometers, we would even do it between 0.1 and 0.3, just to make sure that you purely focus on the microbarometer band. Going much beyond 0.5, you may start to include surf, breaking waves on the coast, especially at I-53, for example, which you have used. They are very prominent. So I would be very narrow in your band. But that's just a remark. A question: what made you decide to use one array element rather than an array average value or some kind of other metric, because you become quite sensitive to the functioning of that one specific element then?
Yeah, that is true. It is strictly been a case of data management and data analysis so far. It would be great to incorporate the data from all of the elements at every site and even do array processing, but that just hasn't been in the scope of our work so far. Yeah, thank you.
In the interest of time, I think we should probably move on. So, Lauren, once again, thank you very much.
Thank you.
Right, so we move on, and I would like to introduce Rodrigo De Negri, our next speaker. He's a researcher at the Laboratoire Magma des Volcans in the University of Clermont-Auvergne in France, and today he'll be talking about the volcanic information system and the use of long-range infrasound monitoring at volcanic eruptions. Floor is yours.
Okay, can you see it? I don't know. I can see it there, but not there. Okay. So thank you, Lorraine, also for introducing infrasound. Very fascinating topic. I want to acknowledge all the scientists. I don't know why it's not there yet. Okay, thank you. That are part of this project. It's not just me. It's a community-based project based by Joe Inquirer. And today I'm going to try to summarize this work in these four parts. A very short introduction of volcanoes at infrasound, and then we'll spend most of the time in volcanic information system. That is what I'm going to mainly, the main point of this presentation, and mention a couple of challenges, what's coming and what has been done very recently, actually. So, well, infrasound basically is acoustic waves below 20 hertz. We cannot hear them, and volcanoes in particular produce infrasound usually around 1 hertz. As it's more or less the range. But volcanoes also produce many other signals too, as here I'm showing you. But when there is an eruption that has an ash column that is sustained, there is a bunch of infrasound produced. The signal has specific characteristics that we are going to exploit for the volcanic information system. But we are not alone. There is many other natural and anthropogenic phenomena that produce infrasound as well. This is one of the main challenges of trying to extract volcanic infrasound from other sources. As mentioned, microbariums is a big one, a big source of infrasound. For me, that's kind of noise. Isn't that how it goes? But when infrasound and volcanoes started to be studied, I think it was from the Krakatoa eruption in 1883. This eruption was so big that was actually seen by meteorological stations in the globe. On the top right corner, there's a globe with black squares that show the positions of these meteorological stations, and the volcano is in a red triangle. And they could be seen at about 4 times passing the wave with non-specialized equipment. So now imagine that the same happens in 2022, that is basically hunger eruption. This was a phenomenon to study from this perspective. There's the IMS now. There are many other technologies that collaborated to study this eruption and characterize it before, during, and after. On the left, you can see how satellite, for example, images are overimposed on the myriad of stations and how each kind of technology, like hydroacoustic or seismic, starts detecting the activity, and then infrasound takes the main lead, and then so on. There are others that come after. Anyways, on the right, you see 4 just IMS stations. You could see about 16 passes of the wave now, not just 4, which is quite amazing to see, an incredible opportunity to study volcanoes and infrasound. Now, this is all thanks to the IMS. I want just to mention this here. Infrasound is just a sub-part of it, but the multi-technology component of it is very important for any monitoring system, really. And when you look at the IMS infrasound array and look at the volcano positions, you see naturally you come with the idea of why don't we use infrasound to monitor the volcanoes in 24/7 way, right? And that's it. That's a volcanic information system. The idea is to do an infrasound-based methodology for remote detection. Here, remote means beyond 250 kilometers nominally. You don't need to be in there. The infrastructure is already working, and let's use it. And why we want to do this is because mainly, well, not mainly, but one very big risk of volcanic eruptions that are going to happen yearly, that are like the volcanic eruptions with a volcanic explosive index 3 or bigger, is that they produce a lot of ash. Ash encounters by aviation are very, very risky, and you want to avoid them as soon as you can to know where is the ash plume when it was generated. It requires a 24/7 monitoring system, and we think infrasound can be integrated in the current systems that are satellite-based. What is this is basically a series of steps to extract the volcanic signal from all the others and characterize an eruption when it happens. So I'm going to use the example of Fuego Cordón Caulle, that is an eruption that happened in my country in 2011 that produced a big ash plume that was sustained. This is a VI4, it's a little bigger than the eruptions at VI3, and it produces a sustained plume about 10 to 12 kilometer heights, affected large areas, especially in the Argentinian side. So if we look at the detections here, and at this moment to mention, I'm using the open access database from the IMS data. You can access this data actually. It's a reprocessing. If you're curious about it, it's great for scientific research. So here on the top right, I'm showing these 3 subplots for each one of the stations, I02 in Argentina, I08 in Bolivia, and I41 in Paraguay. I'm sorting the detections by time in the x-axis in the whole year 2011, and the color is for the frequency. Lower frequency is the blue, higher is yellow. So you see there is a mix of colors there, and on each one of the subplots on the y-axis you see the azimuth with respect to the target volcano. So 0 azimuth means towards the volcano exactly you're observing here. What the main problem you see immediately is that there's too many detections, right? We call this clutter. So this is the first filter, looking at the specific direction of the volcano. Now, first we look into in a little shorter time window, and a week is more clear than, at least for these two IO2 station and I-41, there are detections hitting more or less at 0 degrees, that means towards the volcano, in the time this eruption happened. I'm talking here the stations that are 1,500 to 2,700 kilometers away, so it's quite amazing to see this. Now, if you zoom in into the azimuth, you see that if you were thinking an algorithm to look at the direction of the volcano and selecting those detections, you would fail here. This is why I'm using this case, because the detections are deviated from where they should be. Okay, so there is something we have to take care of here first, and that is that there are winds in the stratosphere that deviate these detections and cause an upper and back azimuth that is not the one that you expect. And this time of the year in June, you had winds towards the east that produce a deviation that is similar to this cartoon here. Basically, there's an offset that pushes the apparent source to the east. If you pre-calculate that, because that can be pre-calculated, and use that instead, you see in now the red line is a corrected, quote-unquote, back azimuth that I expect to have, and those back azimuths correspond more or less to the detections where they are. So now we are able to actually grab them, right? But there are other problems here, of course, there are many, but one of them is that there are local sources. So I was hoping to have a pointer, but if you look at the bottom plot at I-41, in March, just like in between March and May, there's a group of detections that fall in the back azimuth that you expect that are not the main group of detections that correspond to the eruption. If you were looking at eruptions, you may think that there's an eruption, and that's a false positive, and that's very bad for a monitoring system, of course. You need to remove those, and that's what we're going to do now. So we're going to take the amplitudes of those detections and back project to 1 kilometer from the source and look at the theoretical amplitude they should have. If that amplitude is bigger than 500 pascals, we will not consider them, because eruptions don't produce as high as amplitudes at 1 kilometer from the source, most of them. Tonga eruption may have, but most of them don't. So if you apply this filter now, those detections are removed mostly, and you will avoid a false positive, right? Next step is, well, we look now in time, and we zoom back again in some days, and it's much more clear which detections we're selecting. And the final step is to look into the persistency of the signals and calculate the IP parameter, that is a detector, basically, that was developed around Etna volcano, first locally and then for remote distances. So you just consider detections that are persistent enough in your time window to correspond to a volcanic case. Volcanoes are transient events, and also the dispersion in the atmosphere elongates the duration of the signal, which also means you have a more persistent signal, basically, at your station. If you include these two and calculate the IP values and combine them, you see each one of the stations is collaborating to find an IP value above 100, and you can reconstruct the eruption at thousands of kilometers away from the actual volcano. In the bottom plot, in red blocks, you see the different times of the eruption that are automatically found by this algorithm. You can tabulate this, and very nicely, you see you found them in June. Now, there is a thing that I haven't told you. There's a time delay added because the sound is low. Per 1,000 kilometers is 1 hour. So 1,500 kilometers is 1 hour and a half. You will ask yourself, is this useful? And we can say that resoundingly yes. Here you are comparing in blue lines and red lines the IP or the vis monitoring detections for different eruptions. And in a green line, ash plume detection by satellite. In red lines, the official ash notifications to aviation. For several cases, you can actually find these infrasound-based detections before or corresponding to what you would say satellite, and many times before the official monitoring notifications. So we think there's a space here to collaborate with satellite and infrasound, especially to improve and make more robust 24/7 monitoring systems. We have tackled these two challenges, the first two, atmospheric and clutter. Now, just a second to talk about data availability. Currently, it's not possible to access 24/7 IMS data, but we are testing this on the open access data. We hope in the future we can do something to have a more, at least near real-time access to it. But also this can be complemented with local arrays. We hope to do that too, not just IMS infrasound stations. About the challenges, the natural challenges of the volcanic activity itself, infrasound it just tells you the syneruptive period, and you should always combine the technologies that you have to characterize it better as that study. We have already done a workshop in Florence. There will be an open source project that we up soon in that GitHub repository there. It's not yet there, but it will be. We're working on near real-time tests to high reliability, and we want to have a web interface for people to consult this system. So if you are interested, if you have a group of researchers that want to work in this, you have an an infrasound station, that you have locally, and you want to use the data to look at volcanoes, please contact me. There's my email or my GitHub account, and thank you very much for the opportunity.
Thank you very much, Rodrigo. Let's see how many questions have we got for him. Let me just break the ice a bit, and just for thinking from the AMS perspective, the network, we are very proud of the coverage that we have with our network. From your perspective, you use our data purely for monitoring volcanic eruptions. Where do you see in the world places where you would like to have more stations? Hypothetical, of course.
Yeah, I think there was a study, I don't know if it was at ISNE, but I think there was one paper that said that near Indonesia, one station would benefit a lot the community, considering how earthquake prone is the area, or tsunami genic. From my perspective, from South America, I think more stations in the continent would be better. We have all our stations aligned along the Cordillera, which is good for our north-south resolution, but not east-west, which could help a lot. I think it's not a question that I can answer myself. I think, but in my opinion, maybe it would be very beneficial to have a station towards the east of South America. Mm. Yeah, it's a good question. It's a question for a study.
Thank you.
Yeah.
Have you got any other questions for Rodrigo? There in the back, please. Get near the microphone, please.
Hello, Tom Hoffman, CTPTO. I find it fascinating. That presentation was very nice. Actually, the first time I have seen application directly where you say, okay, now take infrasound and get rid of all the problems, and then you find some really useful civil application for it. So this is wonderful.
Thank you.
But I think the biggest hurdle for my thinking always was the time delay, because those waves are very slow.
Yes.
And can you say a word about this? Because you had this chart and say you're faster than others. So is it fast enough, or do we have to have more stations in the network to really use it?
I'm very aware that each one of the infrasound stations is extremely expensive to put there and maintain. So in an ideal world, I would have a much more dense array system, but as I showed you in the last plot, there was a RISE experiment in Europe that brought together national infrasound arrays for a period of time that made our network array in Europe be much, much better than before, right? So what I think could help a lot is to, make this technology more, make more scientists aware this technology could be used in this way. This is something that I'm trying to do now. So they are motivated to put together infrasound arrays in different parts of the world for different purposes. You can use it not just for volcanoes, right? And in terms of the time delay, as I mentioned, I think my biggest problem here was more like the time delay, the 12 minutes of time that I had to present all of this. Actually, that's a very good point, and I think to make other people know that the times of the official notifications to aviation have a big delay that eats out in many cases, the time delay that an infrasound wave can have. So during the time you're analyzing a volcanic event, you are waiting a lot of time and you're gathering information. So during that time, infrasound can come and tell you also, corroborate there's an eruption or not, and can tell you the amplitude and can tell you maybe even a plume height estimate. So the point that I'm trying to make is that each technology has problems and good things, and they should be more integrated. And infrasound, it's ready to be integrated in a different monitoring system as well. It's not the solver of all problems now. Nominally, hopefully you will have stations at 300 kilometers away from the volcano that you are trying to target. That's perfect, and that worked for La Soufrière in 2021, and that's one of the plots I showed there. It was very good, a very good monitoring distance, right? But if you are within 1,000 kilometers, you still have a lot of time in this bigger picture of the processing workflow of trying to generate a NASH notification, right? So I don't think it's that big a problem as it seems to be, basically. Yes.
No other questions on the floor? Quick one.
I've got it, yes, if you can answer really briefly. What matters to aviation partly is the amount of ash and the size of the particles. Are the types of studies you do able to offer any information about that?
What infrasound can do is to tell you there is an eruption happening, the estimated amplitude, so probably you can link that to the kind of activity that you have, and also you could have a first estimate of a plume height, but looking at the particle size is part of a different technology, basically. So how I think about this is that infrasound can tell you very early where is the ash cloud and more or less the height to use basically propagation models in the atmosphere to understand where the ash cloud is going and to prevent accidents down the ash plume. The part of the particle size should come after, right? It could be triggered by this kind of thing, you know. Yes.
Well, thank you very much, Rodrigo.
Yes, thank you.
And our last speaker this afternoon, pleased to introduce Samantha Patrick from the Marine Biology Unit, or Earth, Ocean and Ecological Science Unit of the University of Liverpool, talking about wandering albatrosses.
Thank you very much. So 10 years ago, I got a lift home from my field site with the CTBTO crew who were there installing a new hydrophone. And we came up with this idea on the boat. So it's really lovely to be able to come back 10 years later and tell you about what we found. This is also the first conference I've ever been to where I don't know how much people know about birds. So I thought I'd start with a little bit of natural history. So seabirds are the ultimate globetrotters. They're highly pelagic. They're long-lived. They're mainly monogamous, although a little bit less than the BBC will tell you. They're very slow to mature, so most birds have one chick per year. These birds might then go to sea for up to 8 years before returning back to land to breed. And they're highly reliant on land, so they can only breed on land. So even though they go to sea to feed, they go to sea to migrate, they'll always return back to land. And they cover huge distances. So birds cover large distances both while they're breeding, and then also in the wintering period, birds will leave their breeding grounds. They'll travel distances to find better areas where they migrate and overwinter, and then return back to their breeding areas. And so what this means is they have to cover very large distances over the ocean, which is seemingly featureless to us. So how do they find their way, and what does it look like when they go to sea? So when seabirds are at sea, they're doing one of 3 different things. When birds get to an area that's highly profitable, they'll start to forage, and this is seen in data when birds start to turn in circles. So birds will fly in circles when they're searching for food. They'll then rest, so when they're full, they'll rest on the water, or they rest on the water at night. And then thirdly, they have traveling behavior. So the traveling behavior is when they want to get from A to B, and this is easily detected because they fly in straight lines and they fly very quickly. So how do birds know where to go? Birds need to have information in order to find the areas that they're looking for. So over short distances, they need to be able to find food in localized areas. Over medium distances, they'll need to find these patches of food. And over large distances, they need to be able to find the areas they want to go to, whether this is where they're breeding, where they're wintering. And it's not just finding these areas that's important, they also need to minimize the costs of getting there. So they have to get where they need to go, but they need to get there using the minimum amount of energy. So for this study, we used the wandering albatross. So wandering albatrosses are the largest seabird. They can weigh up to 12 kilos, and they have a wingspan of about 3.5 meters. They're hugely wide-ranging. So in a single foraging trip, a bird might go 10,000 kilometers during the breeding season. They might circumnavigate the globe several times during the winter. And it's been estimated that during their lifetime, they'll fly the same distance as to the moon and back 10 times. They're also highly endangered, so understanding their behavior is also really important for conservation. And because of their size and their body shape, they're highly reliant on winds to minimize costs. And what they do is they use these windy and waving areas to soar, which minimizes the amount of flapping they need to do, and this minimizes the cost of this traveling.
Next one. Clicker.
Okay, so what do we know about the way that they can find their way around? So there's 4 different ways that people think that albatrosses might be able to use cues in the environment. The first way is vision. So just like humans, vision's highly informative. And so if albatrosses can just see where they need to go, this is probably their dominant cue that they would use. They also can smell. So albatrosses and petrels in particular have really good sense of smell. And certain areas of the ocean which are really profitable, that might have certain types of marine organisms, will release compounds, and we know that birds can smell their way towards those areas. It's also suggested that they might be able to use magnetic cues, and we also know that they might be able to use hearing, but all we know about this so far is on very small scales. So we know that if birds are up to 1 kilometer apart, they might be able to hear other birds. So they might see that they're feeding there, or they might be able to hear their calls. But what we know is that all of these cues have their limitations. So what you can see on this figure here is that while vision's important, it's probably only useful up to about 30 kilometers. Some other work we've done has shown that birds can fly towards fishing vessels at up to 30 kilometers, but when the boat's further away, they can't fly towards it, suggesting that's the limit of their vision. Olfactory cues might be more useful over larger spatial areas, but they tend to be very heavily affected by winds. So this means that they can be unpredictable in certain situations, and also that they're not great for very long-range cues because they'll dissipate with the winds. Magnetic cues are useful, but the magnetic field of the Earth is relatively fixed. And so whilst it's useful for a bird to be able to orient, to know whether it's going north or south, it's not very useful to be able to tell it anything about the dynamic environment. So what we have dynamic short-range cues that the birds can use, and we have fixed long-range cues. But we lack a dynamic long-range cue that a bird could use to be able to navigate its way over long distances to look at environmental variables that are changing in space and time. So why might infrasound be important? So earlier on in this session, we had a presentation about microbaromes. And we think that infrasound might be important because it might be able to help birds identify land. So it might be able to help them orient and fly back to their breeding colonies. It might be able to help them find optimal weather conditions. So they like weather conditions that are windy and wavy, although not too windy and wavy. And they also like upwelling zones. So upwelling zones where the water's brought to the surface are highly productive because the food's brought to the surface and the birds can then forage on it. So marine habitats microbaromes are an important source of infrasound. And these microbaromes are associated with waves colliding together or waves hitting shorelines. And because they're generated by strong winds and storms, this is a potential source of really important information for albatrosses. And it could be an indicator of a long-range weather conditions, and it could also be able to be used to identify profitable areas. So to look at this, we used 89 wandering albatrosses. So we equipped them with GPS loggers. So these are just loggers that you might use for sports, or they're just things that you get off the shelf. So we take them out of their box, we waterproof them, and then we duct tape them to the back of the bird on its feathers. So we deploy it when the bird's on the nest, we let the bird go to sea, and then when the bird returns, we take the device off and we download the data. So from this, we have behavior every 15 minutes of the birds while they're at sea. And what I was talking about earlier was we're really interested in these traveling sections. So we're interested in when the bird is making a long-distance movement, and these are the areas, these are the sections of the track when they're flying straight and they're flying quickly. On the map here, you can see the tracks that we had. So the green are the females, so the females go north of the colony, and the yellow are the males, and they go south of the colony. And in the top left, you can see South Africa, and in the bottom, you can see Antarctica. So you can see just how wide-ranging they are. So what we did was we combined this with microbarometer soundscape maps, and what we wanted to know was we wanted to estimate what was the microbarometer experienced by the bird at a point in space and time. And so to do this, we also combined it with wind data. So we used ECMWF wind data. And from this, we looked at the speed and the direction of the wind. So every time we had a position where a bird started this directed flight, we called this a decision point. And then we looked at the direction that the bird flew at that point in time. So here we have our albatross. And what we did was we created 6 segments around the bird. We looked at the segment that was chosen by the bird, and we compared that with the other segments. So we used a radius of 2,000 kilometers around the bird, as this captures about 95% of the microbarometer signal. And we integrated the infrasound across those segments, and then we compared the conditions in the segment the bird chose compared to the segment the bird didn't choose. And this allowed us to ask whether the birds choose segments based on infrasound and wind. So the first result we found was that albatross movement is linked to wind. This has been very well reported previously. So just to understand the results a little better, I've put this schematic just so you can see. So a headwind is a wind that blows straight into the face of the albatross. These are not great, and they tend to be energetically costly, and birds don't like them. Tailwinds blow into the back of the bird and can help it move along with minimal energy. So birds tend to prefer tailwinds. So here you can see on the figure, we're just showing you the results for males, but the results for females are very similar. I thought it's just easier to just show you fewer graphs. So on the x-axis, we have the wind direction. So we have the tailwinds on the left in pale blue, and the headwinds on the right. And then on the y-axis, we've got what's called the odds ratio. This is just the chance of a bird choosing a segment. So the higher you go up the y-axis, the more likely a bird is to choose that segment. And what you can see here is that in tailwinds, birds seem to be more likely to choose a segment. But this is most important at high wind speeds. So on this graph here, the high wind speeds are shown by the purple line. And what you can see is there's a really strong effect in high wind speeds and in tailwinds. So this means that birds like tailwinds, especially when the wind is strong. So what about infrasound? So this figure here is similar. So we have the estimated odds ratio on the x-axis. And if you're to the right of the line, then that means there's a positive effect. To the left of the line, there's a negative effect. And if it overlaps the line, there's no effect. So the first and exciting result we found was that as the sound pressure level increases, there's an increased chance of the bird choosing that segment. And this showed that birds move towards areas of higher infrasound. Next, we thought that wind speed would be important because it's important for other areas of flight. But what we found here was that as the wind speed increased, it didn't affect whether the bird chose the segment or not. So the wind speed didn't affect the selection of the segment. But what we did find was a strong interaction between the wind direction and the infrasound level. And I'll show that on the next slide. So in tailwinds, which are shown here by the blue line, As the sound pressure level, which is shown on the x-axis, increases, the probability of choosing that segment also increases. And that's this blue line that you can see increasing in slope. However, when you look at headwinds, which are shown in the green line, as the sound pressure level increases, there was no change in the propensity to choose that segment. So what are our take-home messages? Well, first, we think this is the first evidence that birds do respond to infrasound. People have speculated in the past that birds may use infrasound to avoid tornadoes, or birds may use infrasound for other reasons, but this is the first time anyone's actually been able to show it in the wild. It does suggest that infrasound may be a long-distance cue for movement, but there's a lot more to do. We need to look at the scale at which birds are integrating the infrasound signal, and what would be ideal would be to study the other cues that birds are able to use to see which of those are being used at different time points. Third, wind direction is crucial, so this is really important. It suggests that birds are only willing to make decisions when the wind is good. So birds will move towards areas of higher infrasound when the wind conditions are optimal. But when there's headwinds, birds don't make those decisions, suggesting that headwinds prohibit those kind of movements. And finally, this is just the start of us understanding the importance of infrasound for animal navigation, and I hope that there'll be many other people using the CTBTO data to investigate it.
Thank you very much, Samantha. A fascinating study. Any questions from the audience? Yes, please. Can you?
Hello. Thank you for the presentation. I have a question. You said that the albatross may be sensitive for infrasound. As you know, the infrasound waves travel long distances because they are trapped in the atmospheric waveguides, especially the stratosphere and the thermosphere. Now we are talking about an altitude above 10 kilometers. And what I know that such kind of bird cannot go more than 1 kilometer, 2 kilometer maximum, I think. So now we cannot talk about infrasound for long distance. As I said, the main waveguides are so high. So I think the albatross is sensitive to the wind direction more than infrasound. Than the infrasound.
Yeah, I mean, I think it's a really good point. I mean, the reason to model the wind direction and the infrasound simultaneously is we can control for the wind direction, so we can control for the effect of wind, and we look at an additive effect on top of that. You're completely right in terms of how the birds that only fly maybe 10 meters above the surface experience infrasound in the way that we know. So we've been doing work, part of the project designed some new loggers that are able to actively record infrasound on the bird, and that's something that I think is going to be really important. So if we want to know what infrasound the bird's actually experiencing, the best way is to record that on a device on the bird, and I think something like that's the best way for us to understand better exactly what they are using.
Thank you. There was a question in the middle, I think. Yeah, you've got a microphone.
Yeah, it's kind of a side question, but when you mentioned long-range navigation cues, I didn't hear you mention use of sight to astronomical observations. And I seem to remember years ago there were experiments putting pigeons into a planetarium and got positive results. What's the current thinking on that?
Yeah, there definitely have been, and there are other navigation cues that have been suggested, so I focus mainly on the kind of the ones that have been very well supported, I suppose, or the best discussed. I don't know that there's been much work recently on that, but I would have to have a look. But yeah, there certainly has been some work in the past, and also work looking at sun compasses as well.
Yeah, thank you.
Any more questions? Oh, if this is really a question rather than a comment.
Yeah, this is a question. Do you have an idea or to do a study on the behavior of the albatross when passing close to infrasound sources? I think this is important if you look to the behavior of the albatross when crossing an area where there are volcanoes or something like this, maybe give you an idea about his sensitivity about infrasound. Do you have such kind of idea or not?
It's not something we're doing at the moment, but the seabird tracking database is a huge resource which is also openly available. So it's possible that if you could find the data, so we did talk about this in the past, if you could find data where birds have been tracked simultaneously to when you have volcanic explosions, then you may well be able to look at whether there's changes in behavior. But it would require quite a good time match in terms of birds being in the right place at the right time and having loggers on. But I think it certainly is, it is interesting, but I guess one question would be, why would they respond to volcanic eruptions? I guess we don't have such a strong biological prediction for that as we did for the microbaron infrasound.
In the interest of time, I think we probably need to finish the questions on this talk. So thank you, Samantha, once again.
And thank you very much to all the presenters and the audience. I just would like to remind you that you can use the app on your phones for voting these presentations. There is in the application, you can see on top, on this session, there is a button on the right-hand side you can use. Also, an announcement for the e-posters will be on Thursday. Thursday morning, we have e-poster sessions, so please look in the app and attend those that are of interest. But thank you very much for your time, and apologies for the delays. Thank you.